This presentation is an analysis of variance, or ANOVA for short. I'm Pat Obi, Professor of Finance and Quantitative Methods at Purdue University, Calumet. In ANOVA, we compare the means of 3 or more populations to see if they are equal. The null hypothesis is therefore a statement to that effect as shown here. Because we compare 3 or more factors, the alternative hypothesis is always worded as I indicate here, since the null hypothesis would be rejected anyways if one of the means is different from the rest. To describe the structure of ANOVA, I introduce this example, which seeks to determine if the average birth weights of babies in 4 African countries are equal. So what you see here is a random sample of baby birth weights for country 1, 2, 3, and 4. And you can see that their sample sizes need not be the same. And what you see here are the sample means. And so in this example, as is the case in every ANOVA, the null hypothesis is that the means are the same. The alternative being that at least one of these 4 means is statistically significantly different from the rest. As a flashback though, you may recall that in the comparison of 2 populations, we would simply take a random sample of observations from each of the 2 populations as shown here. So if, for example, we wanted to compare the baby birth weights for just 2 countries, then the test statistic would be one that is based on the t-distribution. And this, what you see here, is the t-statistic that would have to be calculated assuming 2 independent populations, as you learned from a previous lecture. So here, the alternative, the null hypothesis, is that the 2 population means are equal. The alternative can, in this case, be expressed also mathematically. It need not be worded. It is only in the case of analysis of variance, as I show here, where we have more than 2 means, 3 or more that is, that the alternative hypothesis would definitely be worded. So, proceeding then with ANOVA, the decision rule can be expressed in one of 2 ways. In the first case, we could choose to compare the calculated statistic, which in this case is called the F statistic, to the critical value of the F statistic from the table. So shortly I'm going to show how to calculate this F statistic, which is at the very core of this lecture presentation. And we would reject the null hypothesis of equality of means if the calculated F statistic exceeds the critical value of F. In other words, we reject the null hypothesis if the calculated value of F lies in the significance region, which is also called the rejection region. I will show that shortly as well. The other way is to compare the p-value that corresponds to the calculated F statistic, and we're going to compare that to the significance level, which is the alpha level that you choose to perform the test. Remember, you choose the alpha, the researcher chooses the alpha level, which could be either 0.10 as in 10% level, 0.05 as in 5% level, or 0.01 as in 1% level. And then you would reject the null hypothesis if the p-value that you obtain from your statistic is less than the level of alpha. This is the shape of the F density function. It is a skewed distribution, skewed to the right, that is, positively skewed. The lowest value is 0. And so as you can see here, the F distribution is not symmetric. It's not bell-shaped like the normal distribution or the t-distribution. Now then, if therefore you establish the critical F value, and you come up with a calculated F value that is greater than this critical F value in that it lies within this rejection region right here. you would have to reject the null hypothesis, concluding that one of the population means is statistically different. At least one of them is statistically different. And the f that we calculate is so defined. You will learn how to calculate what's called the mean square treatment, which is a measure of the explained variation in the samples that you're going to be taking. And you divide that by the mean square error, which is a measure of the unexplained variation in the populations that you are evaluating. And so we're going to proceed with this example, which I encourage you to read it up first of all, and then here is the summary of it. So in this study, there are three types of fertilizers we wish to compare their levels of effectiveness. And the way we're going to make the comparison is by looking at the average crop yield achieved with each type of fertilizer. So here there are 5 farm plots. Each farm plot is subdivided into 3 portions, and then each portion would be treated with each of the 3 types of fertilizers. And so for fertilizer type A, these are the average the crop yields actually that are achieved with this treatment, and ditto for types B and C. So you can consider you can consider the 3 types of fertilizers as treatments, which is actually the term used in analysis of variance. So in effect, we are treating these first parcels of land with fertilizer type A, and these are the ones with fertilizer type B, and then finally these ones we treat with fertilizer type C. And then based on the treatments, we achieve these crop yields. These are the total crop yields, and these are the average amounts of crop yields. So to continue, we first calculate what's called the grain mean, which is the average crop yield achieved from all 3 types of fertilizer treatments. The overall sample is 15. In other words, 15 crop yields, 15 observations, if you add up all of these numbers. The number of treatments, we use the notation C in this presentation, is 3. There are 3 types of treatments. And the picture tells you the story of what we're interested in capturing, the average crop yield achieved under each fertilizer type. So now, here is the logical process for performing analysis of variance. Step number 1, you define your statement of hypothesis, which mathematically is that the population means are the same. Alternatively, the alternative hypothesis rather is that at least one of the population means is different. And this shows you a variation of this statement of hypothesis when you word it. So either or is okay in the case of analysis of variance. In step number 2, we calculate explained variation, also referred to as between group variation. So you might see one of these 2 terms in statistical books. However, explained variation is the more generic term. Explained variation is going to look at the differences between each treatment mean and the overall mean, as I show here for treatment number 1 mean, treatment number 2 mean, and treatment number 3 mean. So if I go back here, we're going to be looking at the difference between this mean here for fertilizer type A of 81.2 and the overall mean of 84. So it's going to be 81.2 minus 84. That difference would be squared as I show right here. And when you square it, you then multiply it by the number of observations under group 1 or treatment number 1, which is 5. You do the same for treatment number 2. The sample mean achieved for fertilizer number 2 minus the grand mean. You take this difference, square it, and multiply it by the number of observations for treatment number 2, which is also 5. It is also 5 for treatment number 3. Now, keep in mind, if I were to go back here, that the number of observations need not be the same across the 3 types of treatments. I go forward again. So after you've done this, you calculate it out and it comes out to 137.2. This is called the sum of squares treatment, 137.2. Following, you calculate the mean square treatment. Mean square treatment is actually equal to the sum of squares treatment divided by its degrees of freedom. The degrees of freedom here is C minus 1, which is the number of treatments minus 1. That brings us down to 2 because there are 3 treatments. And this works out to be 68.6. Again, notice 2 things. One is C here is the number of treatments. In this example, 3 of them. Minus 1 degree of freedom, we have 2 degrees of freedom. The second is, if you observe carefully, this calculation is a type of variance. This mean square treatment is actually a type of variance. And as a reminder, this is our definition of sample variance, where we divide the sum of the squared variations by the degrees of freedom when you are provided with sample data. Degrees of freedom with sample data, of course, is sample size minus 1. And in this example, in this case, there are actually sample size is analogous to the number of treatments. The numerator sum of squares treatment, notice if you look at this here, it's analogous to these statements that you see right up here. It's the sum of the squared deviation between, in this case, the mean for each group and the overall mean. And then you're going to multiply it by the sample size. Step number 3, you calculate the measure of unexplained variation. The unexplained variation, also called error variation or within group variation, looks at the differences between each observation and the mean for that particular group. So that for treatment number 1, we're going to be looking at the difference between each value within that group and the mean for that group. We do it for all of the observations, and then these differences are squared. If I go back here to the mothership, as it were, we're going to be looking at the difference between 77 and 81.2, 79 and 81.2, and the beat goes on. And for group number 2, or treatment number 2, we're going to be looking at the difference between 83 and 88.2, 91 and 88.2, etc. And finally, for treatment number 3, we're going to be looking at the difference between 80 and 82.6, this 82 and 82.6, and so forth. So if I continue forward, that's exactly what you see here for treatment number 1, treatment number 2, and treatment number 3. We take these square differences right here, add them all up, and this one, the result here is 80.80. And for treatment number 2, the sum is 78.80. And for treatment number 3, you sum these to get 31.20. You add them all up and you get 190.8. Next, you calculate the mean square error, which is the variance form. In other words, you would be dividing the sum of squares error, which is 190.8, by the degrees of freedom for error, which is defined as n minus c, the overall sample size minus the number of treatments c. And the overall sample size is 15, number of treatments c is 3, 15 minus 3 is 12, and that's your denominator. So when you divide that into 190.8, you get the mean square treatments of 15.9. Step number 4, you calculate measure of total variation, and that's sum of squares total, which is so defined. As this formula shows, you are going to be looking at the difference between each observation and the overall mean, so that each observation, regardless of whether they are under treatment number 1 or 2 or 3, you are going to be looking at the difference between that observation and the grand mean, the overall mean of 84, as you can see right through. And then when you sum the differences, when you square the differences, which will provide you with these results for 1, treatment 2, and treatment 3, you add them all up and you get 328. Now then, in the case of a single factor ANOVA where we are evaluating just one particular factor, in this example, fertilizer treatment, we can also obtain sum of squares total SST by summing sum of squares treatment and sum of squares error, which we already have calculated. For sum of squares treatment, it's 137.2. For sum of squares error, it's 190.8. You add up these two numbers to get 328. And the degrees of freedom for total is the traditional n minus 1, which in this case is 15 minus 1 of 14. And finally, we calculate the F statistic, which is the ratio of mean square treatments and mean square errors, which you see here. Remember, mean square treatment is our measure of explained variation, and mean square error is our measure of unexplained variation. These are the corresponding numbers, which works out to be 44.31. So this is our calculated F statistic, which we must then compare to the critical value of F from the table. So we're going to go to the F table, and let's say we choose the most conventional level of significance, alpha of 0.05. We will find the critical value of F to be 3.885. The critical value of F is based on degrees of freedom associated with the numerator variation, which is the treatment variation, and that degrees of freedom is 2, and the degrees of freedom associated with the denominator variation, mean square error, and the degrees of freedom there is 12. So if I go back here to explain variation, which is treatment variation, degrees of freedom is 2, which I also show right here. And if I go next to unexplained variation, which is error variation, degrees of freedom n minus c is 12. So continuing here, we're going to go to the F table and look up the value of F corresponding to treatment degrees of freedom of 2 and error degrees of freedom of 12. So when you click on that link, you will see a table such as this. There are several tables on the F on the internet, and of course you have the F table at the back of your statistics textbook. So here we're looking for F table, alpha of 0.05. Click on it, and here you have it. And the degrees of freedom is 2 in the numerator. The numerator degrees of freedom are shown here horizontally. The denominator degrees of freedom for error are shown here vertically. So for 2 and 12 degrees of freedom, the corresponding F statistic is this, 3.8853. And that's what you see written here. And so, because our F statistic, which we have calculated, exceeds the critical value of F from the table, we will be rejecting the null hypothesis and concluding that at least one of the means is different. So now, the F distribution looks like this, with our critical value established at this point and the calculated F value of 4.31 somewhere within this significance region, also called rejection region. In the very final step, a lot of times we use the ANOVA table to summarize our results. The sources of variation are treatment, also called explained variation or between. The other is error, also called unexplained variation, and in some books within. I've given you all the good names here. The calculated sum of squares treatment is 137.2, and the calculated sum of squares error is 190.8. If you add these two, that gives you sum of squares total of 328, which as I showed, can either be calculated the longhand or simply add up these two numbers. The degrees of freedom for treatment is C minus 1, number of treatments minus 1, which in this example is 2. Degrees of freedom for error is N minus C, overall sample size minus the number of treatments. 15 minus 3 is 12. And finally, degrees of freedom for total is N minus 1, which is the overall sample of 15 minus 1 to give us 14. Mean square treatment is sum of squares treatment of 137.2 divided by its degrees of freedom of 2, which works out to be 68.6. Mean square error is 190.8, which is sum of squares error, divided by 12, which is the degrees of freedom for error. And most importantly and finally, the calculated F statistic, which is the ratio of mean square treatment and mean square error. If you divide 68.6, which is mean square treatment, by 15.9, which is mean square error, you obtain the calculated F value of 4.31. And so our decision would be to reject the null hypothesis because the calculated F statistic of 4.31 exceeds the critical value of F, which here is 3.885. And our conclusion, therefore, is that based on the sample data, there is evidence that crop yield is not the same for all three fertilizer types.